Welcome to the short week. Woo! Yes. Yes, there are classes Wednesday. Thursday and Friday you have off. Me too. Yes. So, we are into light, and we'll transition into color today. Light's an electromagnetic wave. It's transverse. You can picture this and this as the up and down, up, down as it propagates. It's because its electric field oscillates. It gets stronger, more positive, less positive, zero. Then more negative, less negative, then zero. A lot like the AC circuits. When I do that sine wave, it just increases one way, comes back down, and increases the other way. We've done that with velocity, where it goes up, stops, zero, and then goes back down. But velocity is a vector, so the sign changes. The electric field does that. Well, there's also a magnetic field that does the same thing, perpendicular to the electric. They do it together, and they propagate through space. That's an electromagnetic wave. And we're seeing how those go through things now. How they get reflected, transmitted, or absorbed. And that has to do with the interactions again, and how fast it travels through things. The speed can change. So I ended with going through glass, shining visible light through glass. You know it's transparent. So does this light interact with the glass at all? If it passes right through it, does it have any interaction with the glass? Yes. Yes. Is this the same light as that? Very good. Thanks for paying attention. These are actually different light waves than those. Do they have the same frequency? Do they have the same wavelength? Is it the same color? Yes. Yes. So what's happening inside the glass? When the first wave comes in and hits those particles there, what happens? That's right. You can picture an electron. It absorbs that energy of the wave. The wave is trying to drive the particle at that frequency, driving frequency, because this has a certain frequency. It starts to move. If you're on resonance, what happens at resonance? You get absorbed. That's where it likes, its natural frequency is that driving frequency. They match up. And so it absorbs that energy, and the amplitude increases. So that particle would start moving a lot more, and thus it would heat up. It would transfer into heat. But the light wouldn't come back out either side if it's absorbed. That's what ultraviolet and infrared light do. This one drives the resonant frequency of the electrons. And this one drives the resonant frequency of the molecules for glass, most glass. So they get absorbed on resonance. How about a mirror? Is it transparent? No. Is it opaque? Yeah, light doesn't go through. That would be opaque. But the light doesn't get absorbed either. It doesn't go through and it doesn't get absorbed. It bounces back at the same angle it came in at. So what's going on there is the electrons of most metals, it's like there's probably a thin coating of aluminum or silver behind this glass. And it'll absorb that energy, but those electrons are loosely bound to the atoms that they're part of. That's how metals can conduct heat well and electricity. So it doesn't transmit through the material because those electrons are kind of on the surface free. So they absorb it, but they don't like it. They give it right back off. A different wave with the exact same frequency, wavelength, color, and that's reflection. That's what happens when something reflects. So, you know, you can fix your hair. So the light comes in, it absorbs, but then turns right around and re-emits it back out instead of through it. where I did my little dance Friday. You know, here comes the wave, and bloop, the atom absorbs it, and it gives it right back off at the exact same frequency. And that would transmit through it. If it comes in, bloop, and spits it back out that way, it's a reflection. Does that make sense? Yes, it does. The energy is conserved. Basically, electrons are at different energy levels, and you can think of them as they absorb the energy, they get boosted up to a higher energy level. They don't like being up there. It's not stable. So they give off the exact same amount of energy to fall right back down to where they were. So the amount of the energy it takes to get from here to here, whoop, it absorbs that to do so. As it falls back down, it has to give up the exact same amount of energy. So it's the exact same wavelength and frequency and energy of light that came in. If you remember your chemistry with electron orbiting energy levels and different orbit levels, it's that idea. Let's make a little table here. Whoop, this one. So, at resonance, light is absorbed because the driving frequency matches the resonant natural frequency. Thus, the internal energy increases. Otherwise, I mean, where did that energy go? It was absorbed by the material. Off resonance. Okay, the driving frequency, the incoming wave, does not match the natural frequency. Well, then it is re-emitted. And it can do that two ways. It can pass through, and we call that transparent. And it can reflect back. Obviously, that's opaque. Most things reflect. This table reflects. The carpet even reflects, not as well as the table. It's all on how much gets absorbed versus how much gets re-emitted. And does it re-emit through? It's kind of, you've seen translucent things, semi-transparent. You can have all kinds of things. We drew this before. If you have the surface of water, air and water. You know water is transparent, but if you have a light coming in, you can see a reflection, and some gets refracted, and thus transmitted through. So you can have a mix of these things, depending on what the material is made up of. Mirrors almost entirely reflect everything, but not completely. They absorb a little bit. Mirrors are not 100% perfect reflectors. It's one reason they use prisms in binoculars. With that is something called total internal reflection. Once it goes inside it, 100% of it's reflected back. Not 99.9 like a mirror maybe, because some of it will get absorbed. With a prism, you can get all of it back. Questions, comments? This kind of drives the next part with color, so I just want to make sure we're making sense with these interactions. So then, here's the speed of light, a really, really fast number. That was introduced with relativity. And here's an idea. If the speed of light in a vacuum is that. The speed of light in air is essentially that. It's hardly affected. In water, though, it's 3/4 the speed of light. It slows down. Now, what did I say about speed for light? It's a constant. It's always this. So what does 3/4 the speed of light really mean? Because light isn't actually slowed down. It does not travel slower than this. So what's happening inside water? It's interacting with the molecules and being delayed in between molecules. You know, the bloop, light travels from here at the speed of light over to this molecule, bloop, but it has to absorb it and then re-emit it. That takes time. And then bloop, speed of light over here, absorb, re-emit. So they get delayed with each interaction. So the total time it takes to get through the water is slower than if the water weren't there. So I'm just trying to reiterate, the speed of light's a constant. But we say it takes time to go through water, so it's as if it traveled 3/4 the speed that it does in a vacuum. Make sense? Okay. You can see glass is a little slower, about 2/3 the speed of light, and diamond's even less than half. One reason they're so sparkly, the different angles that they can refract at. The speed, remember, the speed changing is what causes refraction. So diamond, where it slows down the most in these materials, gets refracted more. It gets bent, deviated from its straight path more. It has to do not with mass, but interactions is the key. Now, a lot of people, you can translate that to density, but if you always just go off of density, it doesn't work. Diamond is more optically dense, if you will. In other words, think of a person trying to get through a crowded room. You run into people, so it's going to take you longer to get through the room. Diamond's like that for light, as opposed to an empty room. It's those interactions. All right. Before we move on to color, we're going to start blocking light and things. Shadows. There's two terms you might not be familiar with. If you have a light source, we know light comes off of it. Here's a few beams. I've drawn 4. Let's look at this one. It comes along at this angle, just clears the object, and so light hits the screen over here. You're like, duh. Same with all the other rays. Light that goes this way doesn't hit the screen. Light that comes over here does hit the screen. Light that comes over here hits the screen. But in this region, there's some light that is blocked. Let's look at a light ray that comes like this. Boom, it doesn't hit the screen. And so there's less light in this region. Well, these two rays, the ones that come along here and just pass, all light inside of there never hits the screen. Nothing ever hits the screen there. It's a shadow. It's called the umbra. That's what you'd expect. It's dark because no light hits the screen there. However, there's also this penumbra. It's kind of it's dim. It's like gray. It's partially lit, partially dark. And that's the light that, okay, it doesn't get blocked hitting the object. This side gets blocked, but light from this side can still hit there. Can you see that one? Some light can hit there from one side of the object, but not the other. That's why it's partially lit. That's called a penumbra. You've probably noticed it, just didn't know what to call them or cared. So let's make a shadow. Here's my light source. Beautiful. All right, doink. Let me get my... Can you see it's fuzzy around the edges? It's partially lit, like right there. But right here is the umbra. No light is hitting there right there. Well, from this light source. There's obviously those lights are. But I won't put you in utter darkness. So that's the umbra. But the penumbra, see, it looks like my fingers are skinny. Depending on, like that. Just the dark part, the umbra is really narrow, but the penumbra is right in there. There is an umbra right along there. You can see where it's a lot darker? Or this one, a lot darker. That's the umbra. So my finger is blocking all light from that spot. but there's light from one side of my finger that's getting blocked compared to the other side of my finger that's not getting blocked, and that's the penumbra, the fuzzy part. You with me? So that's the terminology for shadows. My hand is opaque. You see my hand. Because you can see it, that means some of the light's reflected. So there's some particles that absorb and re-emit back out to you. There's others that are getting absorbed because it's opaque. It's not letting the light transmit through it. And so, you know, if you leave your hand here long enough, you know, I can feel the heat. It's because I'm absorbing that light. It's making my particles move around, and that causes heat. Here's something fun. If you get closer to the light source, it's fuzzier. The penumbra is bigger. It's just kind of a perspective thing. The light around from the two sides can overlap even more. And so it's a fuzzier image. But if I get farther away, look what happens. It looks like a sharper shadow, doesn't it? It's almost all umbra. Some of you in the front row can probably see a little bit of the fuzziness on the edges. That's the penumbra. But just look at the angles. The farther away I get from the light source, the closer that looks like a point light source instead of spread out like a big wide sun. But, you know, if you're out at Pluto, the sun looks like a little point light source. So Pluto would cast a sharp shadow, where the Earth casts a fuzzier shadow because we're closer to it, and so it looks wider. We can get light from the two sides. That's shadows. Here's just a circle. Not too complicated there. Now, one of my all-time favorite subjects, color. I just love color. So if I get a little giddy, I just apologize now. Did that, did that, did that, did that, did that. Let's start with light shining through. All right, hey, let's get one. Can you guys see what color this is? How do you know that? Here, you can see this. What color is this? White. Do you guys know what colors make up white? All of them. So this puts out all wavelengths of visible light. So if I shine it through the blue light, what color do you now see? Blue. So is this opaque or transparent? Right. It's both. It's transparent to blue. Blue light is not absorbed. Hence, you see it. It makes it to your eyeball, and your brain goes, hey, I see blue. What colors are not transparent to it? Everything else. Visible. Yeah, so like red and green and yellow and all that are getting absorbed, which tells us what about resonance? They're at resonance. Light is absorbed. So the pigment in this glass, the dye in this glass, resonates with all colors but blue. Thus, it absorbs them. Blue, it doesn't, and it lets it pass, and you can see it. Now let's try this one. If I reflect this light off the surface, so I can see the flashlight, what color do you think I see? Got one vote for white, but this is a blue piece of glass. I'll hold it up so see if you guys can see. If I change my angle, can you guys see that? Can you see what color it is? You guys okay over here? See, it's blue to me right now, but what color do you see? Why is it white? Not just perspective. It's a reflection. The light comes in, hits the surface. Yeah, it never changed mediums. The light that reflects off the glass never went through the glass. So it didn't absorb the non-blue colors. It reflected some of those. Remember, all things, this is partially reflective, otherwise you wouldn't see it at all. None of that light went into here. None of it got subtracted or added or anything. All of the wavelengths can bounce off of this, and so it comes back to your eye, all wavelengths, all frequencies, all colors. It still looks white to you. Does that make sense?
So is this an example of like the blue light and the white light? How if you put one light wave through it and the other side is not the same light wave? Because it's blue instead of white.
I didn't follow all that. Just do it. Try again.
Actually, you were saying how when you shine light through glass,
Yeah, we shine it through, you see blue. But the light that comes out of here is not the exact same light you're seeing.
yeah, it's like a different wave.
Right. Right. Same with reflection too, though. The light I see reflected, it does get absorbed, but then spit right back out from those surface ones. And it spits all wavelengths out, at least somewhat. It is a dimmer white light because some of it's transmitting through and getting absorbed. So it's not as brightly reflected as it is this way. Ow. So that's the pigment in here, is resonating with all non-blue colors. Same idea with a different color. Let's now look at all the different colors. Let's try, let's see if that's dark enough. All right. So here's a blue light. Can you guys see that okay? What color do you think the shadow will be? If I put my hand in front of it, will it be a blue shadow? Oh, yeah, it's black because it blocks black. And you still get an umbra and penumbra. See the slight fuzziness around the edges? This is an LED and it's really, really small, so it's a point light source. But even if I get close, you can see a little bit of fuzziness. So we still get shadows, opaqueness. Same with green and red. I think I'm going to get a little closer. All right. What color, if I add green with blue, what happens? I'm going to overlap green and blue light, add them together. It's this color called cyan. Cyan. By the way, I'll get to it. Now what color will the shadow be? Black? It's green, blue, and black, depending on where it's at. Where's my laser pointer here? So right here, obviously blue light's getting to the screen, reflecting off the screen and going back into your eyes. Well, that means green light must be getting blocked from right there. Well, the LEDs aren't in the exact same position. They're displaced slightly, so they come from different angles. It's like different sides of the light source. So green light can get there and here. Green light can't get there, but it can get here. Blue light can get here, but not here. So where they're both blocked, you get black. It's subtracted. They're absorbed by the circle. But some of it can pass there and there. What color is blue and red? It's a color called magenta. Magenta. And it also does a similar thing. You block it. The red light is blocked from there. The blue light is blocked from there. But those two add to make magenta. What's left? Red and green. What do you think we get? It's my favorite. That one, most people, if you've never seen this, will go, what? And again, you can get red and green shadows. So red light combined with green light makes yellow. So the primary colors of light, who's an artist? Raise your hand. Forgive me, some artists really hate this. Because, wait, what are we all taught as kids? The primary colors are red, yellow, and blue. Red, yellow, and blue. In terms of light, that's not right. Light, the primary colors of are red, green, and blue. Because if you combine all three of them, you can get any other color. they add together. These are the additive primaries, the additive colors. See, all three together is white. And here's my all-time favorite thing. You ready? What's the shadow in the middle? It's all three. I love that. So like right here, where it's cyan, what color is being blocked? Red. Very good, because cyan was made up of blue and green. So if you don't have red, you get cyan. Subtract red from white light. Block the red light from the white light. You're left with cyan. Here's yellow. That's red and green. See? Red and green make yellow. So this is blocking blue light. Here where it's red, it's blocking blue and green. So only the red makes it there. These colored shadows are awesome. Anyway. That's the additive colors for light. Now let's look at a few absorption things. Here's a white piece of cloth. We'll put it in the middle. See, it looks white. So that means it reflects red, green, and blue back to your eyes because you're getting all three. What if I put it over in cyan? What color do you think you'll see? Cyan. It reflects cyan back to you. It reflects green. Reflects yellow. What if I take a yellow piece of cloth? This is yellow. So what colors are making it to your eyes? Green and red. Your eyes actually respond to three colors where they peak. You have three sensors in the back of your eyes that respond to color. And they peak in the red, the green, and the blue. It's another reason why it works out physiologically that the primary colors of additive light are red, green, and blue. So this is reflecting red and green back to your eyeball. It's activating your red cones and your green cones. They both send a signal to your brain, and your brain goes, ah, red, ah, yes, and green. I see yellow. We call it yellow. What color is being absorbed by the pigment of this cloth? The one that's not reflecting off. Blue. It's resonating. It gets absorbed. So let's put yellow over in yellow. No surprise. Let's put yellow over in blue. It absorbs blue, right? See how it looks dark? If this was a perfect shade of yellow, that shade, perfect, it would be completely black because there's no red and green here to reflect off. It just absorbs the blue. Let's try green. Here's a green cloth. So if we put this in red, what do you expect to see? There's no green light over here to reflect. This only reflects green light, mostly. Right? That's why you see green. It doesn't reflect red. It doesn't reflect blue. It absorbs red and blue. They resonate with it and get absorbed. So it only reflects green. So if over here you don't have any green light, there's nothing to reflect. So it looks dark. Make sense? Let's try another one. How about let's try this shade of red. Can you tell it's red? So what colors are being absorbed? Blue and green. So let's put it over in cyan. What do we expect to see? This absorbs blue and green. Cyan is blue overlapping with green. Those two added together. Oh, and there we are. It is indeed black. If we put it over in yellow, what do you expect to see? Yellow is red and green. Oh, there is some red in there. It is a darker red. A little bit. But yes. You get in this game? Over in magenta, that's red and blue. So there is red in there. We should still see red. It's not much darker. This must have more blue in it. How about orange? That one's fun. It's my all-time favorite color. Any guesses what orange is? Before I get to it, let's see if this works. I'm going to dim each of these lights a little bit. All three are dim. Whoop. Just have them come on. Whoop. And whoop. Now what color's in the middle? This color. How many of you want to say white? Because you know it's supposed to be white, but it's not as bright, is it? What do we call a dim white? Gray. Gray. You can get shades of all of these colors and balance them differently. So let me play around with that. I happen to already know that. Let's get rid of blue. Here's red and green. If I dim the green, it's orange. So orange is actually red light and green light, just less green than red. Again, I'll brighten up the green. There they're equal. Red and green make yellow. Dim the green a little bit, and you get orange. If I dim red a little bit, it's kind of this lemon yellow, right? I don't know, everybody calls them something different. Name a color. Let's see if we can get it. What? Lime? Oh boy. It's a challenge. Maybe there-ish? Let's try people like purple, right? Well, there's magenta, even. Let's dim the red. So purple is red and blue, just less red than blue. So it's all because they add together. Light is combining. And all together make white. Let's try subtracting now. Let's subtract colors. So here's the three primary colors of pigments. These are the subtractive colors, or you can call them the secondary colors of light. Red, green, and blue are the primary of light. Cyan, magenta, and yellow, those complementary colors that we got when the additive colors overlapped, these are either the secondary colors of light or the primary colors for subtraction, for pigments. Artists learn this. This is what we learned. What are the primary colors, little Timmy? Red, green, and blue. I mean, red, yellow, and blue. Sorry. Red, yellow, and blue. I mean, you usually don't ask little Timmy to say, can you say magenta and cyan? But these are the true forms. These are the colors used for printing because they subtract light out. What color does cyan subtract out? What color makes cyan? What two colors of light make cyan? Blue and green. So there's red, green, and blue shining on the screen. I'm going to force that white light to go through this filter. What two colors make it through? Blue and green, because you see it. So what color is absorbed? Red. Cyan is like not red. It blocks the red. It absorbs it, so it subtracts it out of the spectrum. What does magenta block? Green. Red and blue make it through. Red and blue make it through that. Blue and green through this. Which one will make it through both? This one's blue and green. This one's blue and red. Blue makes it through both, doesn't it? Look at that. Blue. Let's do yellow blocks which color? It lets red and green through because that's yellow. So it's blocking blue. This blocks blue. This blocks green. So what's the only one left? red. It's common to both of them. Red and blue, red and green. Red. Let's do all three. We overlap them, and there's the subtractive colors. Yellow's red and green, cyan's green and blue. So green's the only one that makes it through both. Nothing makes it through all three, because this blocks red and green, this one blocks blue and green, and this one blocks red and blue. So they're all blocked if they all overlap, and you get black. All wavelengths are absorbed right there because it went through all three filters. And well, these aren't, it's not a total, utter dark black because these aren't perfect and there's other lights in the room coming from just there. But you can see it's dark, right? Questions? Yes?
So if you need all the colors to make black, then why does it cost more money to print in black than it does in color?
It takes more...
It costs more money to print in color than black. Sorry.
Why does it cost more money to print in color versus black?
Right, you need all the colors to make black.
I don't have a great answer. My first would be, well, if you're going to... I don't have a good answer for that at the moment. If you look on the sides of food boxes or magazines or the funny papers, you usually see like in the margins somewhere the different colors used in the printing, the actual inks or dyes. If you have a color printer, often you have cyan, magenta, and yellow because those are the inks you need. And you can combine them. They have now pre-made stuff. They've mixed them, and you might see cyan, magenta, yellow, a different shade of red, a black, maybe a gray, another orange. That's how they got all those. Just if they have them, you can shortcut your printing that way. But why does it cost more? I don't have a good answer for that at the moment. But the bottom line here is pigments absorb light or transmit it. Thus, they can subtract out light. Light is what we actually see, so it's an additive process that responds to the red, green, and blue sensors in our eyeball. Here's one last example with the lights out. Here's 4 transparencies overlapped on top of each other of that building that was next to where the planetarium, exploratorium lived in San Francisco, the art museum. And you can see lots of colors. But if I just take the individual ones, here's just cyan, just yellow, just the magenta part. And black counts for shading and detail. So just black and cyan. Magenta. Let's add yellow. So I've left out cyan. So see, we can get a green in there. It's kind of yellow-green. Starting to get some reds, oranges. But there's no real blue in there. Let's switch the yellow out for the cyan. Now we can get some blues. A little bit of the green, still got some red hue in there, but they're not as strong. You can combine them all though. Just print them on top of each other and that's how you can get an image. Let the light through that you want and block it where you don't. I know why the lights are still out. Let's do this one. You remember our AC/DC LED thingy that I spun around? It had 2 different LEDs in it. This one has LEDs in it too. What color is the ball? Yeah, it's hard to tell. It's kind of whitish. It's maybe a little more magenta than the others. Well, there's 3 different LEDs in there turning on in succession. And what do you think they are? Red, green, and blue. Because together, If they blink fast enough, our eye sees them all at the same time, and this looks whitish. If I spin it, you can see that when they blink on and off, it's in a new position, so we can isolate the three colors. And you can see the red, green, and the blue. If I go slow enough, they can start to overlap, and you can start to see those secondary cyan, magenta, yellow colors. And if I stop completely, they're all in the same spot, and it's a lot more white. The red's probably a little strong on this guy, and so that's why the overall is kind of looking magenta-ish. I like that. So, you know, when you go to raves and do the dances, and they used to have those, and they'd spin them around like this. That was a cooler way to do it instead of just a continuous light. If anybody went to those. Let's split up the light. Since white light is made up of all the colors. See my white light on the brick over there? There it is. All colors. I'm going to send them through a prism. What's the light going to do? It's going to slow down because it's going through glass. And the interesting thing, which color do you think slows down the most? Colors have different frequencies, so they're vibrating at different rates. Who vibrates the fastest? Who has the longer wave? Red has the longer wavelength, so it's vibrating more slowly. Blue are shorter waves, vibrating more quickly. It's the interactions that slow them down. Who's going to have more interactions then? Blue. So blue will get slowed down the most, and thus refract, bend the most. They're trying to go over there, but look who gets bent away the most. Blue. It has a shorter wave, it's vibrating more quickly, it has more interactions, and so it gets refracted the most. That's how a prism works. It spreads the white light up into its constituent colors. And we say, you know, people go, oh yeah, I see red, and I see orange, and I see yellow, and maybe a green, and a cyan, and a blue, and purple, and they get all those fun colors. You now know our eyes respond to red, green, and blue. So look at it as three strips of just red, green, and blue, but they overlap. What's yellow? That's where red and green are both hitting. So it's like the red's right here, but the green's right there. See, they overlap. Same with the cyan. But it spreads them out because they're going different speeds through the glass. If I change the angle of the prism, I can spread them out a little further even. But remember, blue gets refracted or bent the most because it slows down. It's delayed the most going through the glass because of all those interactions. Here's a piece of slag rock. It's kind of translucent. Here's my white light again. If I shine it through this, what colors do you see? Oh, several of them are coming around. What do you see from this perspective? Yellower? So what's that tell you? Reason this through. We got red, green, and blue coming in, but you're getting yellow out. Transmits yellow, which is red and green. So what color is being subtracted out? Blue. And in this case, it gets scattered. It's reflecting out. Check this end out. What color is it mostly? Blue. Can you see it sideways? The side neck closest to the flashlight, does it look bluer to you? That's because they're getting scattered out. And if you remove blue from the white spectrum, you're left with red and green, yellow. Just remind you of any natural phenomena that happens every morning and evening? Sunset. That's how they work. When the sun's high up in the sky, it has to get through the atmosphere before it gets to our eyeballs. What color do you think gets scattered out a lot? Blue. That's why the sky is blue. The size and type of the particles up there react with the short wavelengths of blue, and they get scattered. Thus, the blue doesn't make it to our eyeballs directly from the sun. But red and green do. So the sun is yellow. If you go out into space, what color should the sun be? White. Now, when the sun gets lower in the atmosphere, like in the morning when it's rising or setting in the evening, it has to get through more of the atmosphere. Can you see that? It's lower on the horizon, so there's thicker, more dense atmosphere and particles it has to get through before it can get to our eyeball. More interactions. So not only is blue scattered out, what's the next shortest wave? Green. Get rid of blue and green. What's left? Red. And there's your sunset. So it's all about what colors add up and subtract. Which ones combine when they make it to your eye. Use these reasoning skills on a lot of the homework questions. Here's some paraffin wax. What color is it? Yeah, it's white. What's that tell you? Things that are white, this is reflecting all wavelengths because you're getting red, green, and blue back to your eye. Thus it looks white. If I shine light through it, it still looks white. That means this scatters and reflects which wavelengths? All of them. What color are clouds? White. What makes up a cloud? Water molecules of all kinds of sizes. The small ones scatter the blue, the short waves, and the bigger ones scatter the red waves, which are longer. So it's made up of all kinds of types of sizes. So is this wax. And it'll scatter the red, the green, and the blue, and it looks white. So let's see. Your scarf. Can you hold that up? You don't have to take it off. You can just hold it. What color would we say this scarf is? Purple. What do we know? Blue and red are reflecting off of this. Because it's kind of like magenta. Let's start with magenta. That's blue and red. So they're reflecting off of this. They're not at resonance. So they're absorbed and then re-emitted back out. It's opaque. That's obvious. And it re-emits red and blue. Gets to your eyes, activates the red cones and the blue cones, and your brain says, ah, magenta-ish. Now this looks a little more purple. So there's a little less red that it reflects than blue. What color is being absorbed? Green. The dye in this resonates with green wavelengths, and it absorbs them, subtracts it out of the spectrum, and you get the color you got. I'll stop there unless there's last-minute questions. All right, I'll see you Wednesday.